Welcome to The Explainer. Today, we're going to get right down to the bedrock of, well, pretty much everything. We're going to understand the tiny, invisible switch that makes your phone, your computer, and just about all modern electronics actually work.
So let's just start with the puzzle. Think about your phone. You've probably got it right near you. It's got this tiny little battery, right? But somehow, that little thing powers a super bright screen, a crazy powerful processor, and sends signals all over the world. How in the world is that possible? How can you control so much power so efficiently?
Well, the secret isn't one giant, powerful component. Nope, it's the complete opposite. It's an entire army of millions, sometimes even billions, of microscopic switches all working together perfectly in sync.
And that microscopic switch? It has a name, the transistor. Our whole goal in this explainer is to figure out how this fundamental building block works in its most common job, as a simple digital on and off switch.
Okay, so here's our game plan. First, we'll use a really simple analogy, the electronic faucet, to get our heads around the idea. Then we'll meet the star of the show, the BJT. We'll look at its two basic states, build a little circuit, and finally, we'll meet the rest of the transistor family.
To really get this, we're not going to start with electronics at all. We're going to start with plumbing.
Yeah,
Plumbing. Let's just think about a normal water faucet.
You know how a faucet works, right? A tiny little twist of the handle can control a huge gush of water. A transistor works on that exact same principle. A tiny low-power signal, that's our handle, is used to control a much, much larger flow of electricity. That's our water.
All right, enough with the plumbing analogy. Let's move on to the real deal and meet the star of our show today, the bipolar junction transistor, or as everyone calls it, the BJT.
And this is where it all clicks. Our faucet analogy maps directly onto the BJT. The handle that does all the controlling, that's called the base. The main water inlet where the power comes in, that's the collector. And the spout where it all flows out, that's the emitter.
So here's the magic trick. You ready? We apply a small current to the base, and that opens the floodgates for a much bigger current to rush from the collector through the transistor and out the emitter. We control the big flow with a tiny little flow. Now, a transistor can do some pretty fancy things, like amplifying audio signals, but for digital electronics, for computers and phones, we really only care about two simple states, fully off and fully on. That's it.
First up is the cutoff state, and honestly, it's super simple. If we give the base less than about 0.7 volts, nothing happens. The transistor is fully off. It's just sitting there like an open switch, completely blocking any current from flowing through.
But what happens when we apply more than 0.7 volts to the base? Well, that's when we hit saturation. The faucet is thrown wide open. The transistor flips to fully on, and it acts like a closed switch, letting the maximum amount of current flow right through.
And that's the whole game right there. To use a transistor as a digital switch, all we're doing is flipping it back and forth between these two states, cutoff and saturation, off and on. You could even say 0 and 1.
Okay, theory is cool and all, but let's actually build something. We're going to put this transistor to work and use our BJT to control a simple light-emitting diode, an LED.
The setup is actually pretty straightforward. Remember our faucet? The emitter, our spout, connects to ground. The collector, our inlet, connects to the thing we want to power, in this case our LED. And finally the base, our handle, is where we'll send our control signal.
Now hang on, you might have noticed that little component mentioned in step 3, the base resistor. It looks kind of boring, doesn't it? Just sitting there? But I promise you, it is absolutely critical. So why is it so important? Because if you connect your signal directly to the base without that resistor, it's like trying to turn our faucet handle with a giant wrench. You're using way too much force, or in this case, current. The poor transistor will try to suck in all the current it can, and it'll burn itself out in a puff of smoke. Not good.
So think of the base resistor as a bouncer. Its only job is to limit the current flowing into the base to just the right amount, just enough to flip the switch fully on into saturation, but not so much that it breaks the whole thing. It's a protector.
So we've gotten to know the NPN BJT pretty well. It's a fantastic little workhorse. But it's important to know it's not alone. It's actually part of a much bigger family of components, and each one has its own special talents.
The other huge name in the game is the MOSFET. The key difference is actually pretty simple. While our BJT is controlled by a little bit of current, a MOSFET is controlled by voltage.
This means it takes almost zero power to keep it on or off, which makes it incredibly efficient. And that efficiency is why there are billions of MOSFETs, not BJTs, packed inside the processor that's running your computer right now.
And even within the BJT family, you've got some cool cousins. There are PNP transistors, which are just the functional opposite of what we've learned. Think of it as a faucet that turns on when you let go of the handle instead of turning it on. Then you have Darlington pairs, which are basically two transistors crammed into one package to create a sort of super transistor that can handle heavy-duty things like motors.
All right, let's boil all this down. What are the key things to remember? 1. Transistors are basically just electronic faucets or switches. 2. For BJTs, a tiny base current controls a huge collector current. 3. Saturation means on, cutoff means off. And 4, and this is the big one for practical stuff, always use a base resistor.
So look, you can now control one switch. But what could you build with a billion of them? The answer is everything. By understanding how to turn this one simple component on and off, you've really grasped the fundamental principle behind every digital device you own. The operation is exactly the same, whether you're just lighting a single